How you doing? It's Alan, section 3.2, expanding on what we just explored about this new concept called a derivative. We're now going to define it as a function. So without further ado, let's get to it. So since we just talked about what the derivative finds for us, remember that was the slope of the tangent line, and we focused on at a specific point last section, also gives us our instantaneous velocity. And how to find it, which remember was just the limit of the thing we called the difference quotient. Well, now we're not going to just define it and find it at one single point, but with even more skill, it would be better for us to find the entire domain of our function and what the derivative or rate of change is for the entire function. So that takes us to our first definition in this section, 3.2, number 1, where we define the derivative of a function, which remember we said we would use the symbol and say f prime, and we will define it as, remember we talked about any of those three slope formulas. We're going to focus in on the one called the difference quotient. So see if you can write this down before me. If not, here it comes. So this is our definition of what a derivative is for an entire function. And remember, this is the symbol we use for the derivative, and this is the process that we will use for the derivative. Remember, this is just a fancy way to write the change in our y values over the change in our x values, which is just h. And we want to make that gap between them, that h, approach 0. And that requires a limit process. So this is a way to do what we just did in the last section, but for an entire function to find its rate of change or slope of the tangent. So as we discussed at the very beginning when we introduced what calculus was and who actually came up with it, Newton and Leibniz were the two that were supposedly the godfathers of calculus. They founded it in almost the exact same time in different parts of the world. And so there are unfortunately others that also had some ideas with these types of mathematics. And because of that, we use several different notations. So I'm not going to give them all to you in their namesakes, but I will give you a few that we will see most commonly. And Leibniz notation is typically the one that is used most widely. Here are the first few that we will see, and I'll leave the last one there for Leibniz notation. This one should look familiar. This is virtually the same thing, just not knowing whether the original is a function or not. And this one looks a little weird, different, as does this one. Now, you may be wondering why they look like this. No pun intended. But dy dx, if you remember, the derivative is virtually our slope formula with a little bit of movement, that limit idea. Because we know the slope formula is the change in our y's over the change in our x's, we always look for a way to write things more succinctly. So we came up with the delta for the change. Well, remember, delta is just like a lowercase d in the Greek alphabet. So that means for us, we are virtually writing the same thing. Now, obviously, there is a difference because these are the deltas and these are our d's. We know that this is simply the change in the y's over the change in the x's, or our slope, where this means a bit more, the derivative. So unfortunately, we know that the slope formula was that of a secant line, but we want to find the slope of a tangent line. And so what we are going to do to make sure that we recognize the difference is virtually take the old version for a secant, and we're going to make that difference approach 0, which gives us our derivative. So the way that you can remember this is pretty simple. The old Greek letters finds our old original slope, where the newer alphabet, the lowercase d's, represents more It's the newly defined concept we call the derivative. Okay, so the old stuff, slope formula. The new variables, the d's, is the new concept, the derivative. And because we can now classify the derivative as a function, well then what follows are the graphs of functions. But of course, because we're going to be dealing with a bunch of different functions, there's not really a way to find a basic shape like we've done in the past. Because as you can see here, there's several different types of functions. Say we had this parabola or this absolute value, or even a cubic function or a quartic polynomial. We want to be able to also look at these and find the derivative function as a graph. So I'd really like you all to pause it right here and see if you can at least come up with some part of the graph, if not all of it, for each and every one of these for the derivative of each. And just as a reminder here, I gave you a little hint. Remember what the derivative finds for us. We found last section, if we were to say this point right here at -2, the derivative of that would be the slope of the tangent right there, which is definitely a negative value. What would it be at -1? Well, still negative, but not as negative as this was. And hopefully you can see as we move throughout, it gets less and less and less negative to a point where it will actually flatten out and become 0. So there's your hint. See if you can pause it at this point. Go ahead and try to come up with the graphs of each and every one of these. All right, hopefully you came up with something for each and every one of these. If not, this is a pretty abstract concept. It's not that easy, but it will get easier with practice. Really try to comprehend what we're doing here, not just graph these and get the quote-unquote answer. All right, let's start with the parabola and take a look at what its derivative functions graph would look like. Now, I just plotted a bunch of points on each and every one of these. I can't find the actual derivative of these unless I'm given the function, could do that whole limit process, and that still wouldn't be that fun. So what we're trying to do is just do it graphically without having to do the limit process and the algebra behind it. We just want to stick to geometry since that's what we were given. So we do know that at each and every one of these points, there is a tangent line. And what we're looking at is what it would be, not what it actually is at that x value. So at this one, like -2.5 or 2.25, I know that at that x value, slope of my tangent would be some negative value. So if I was to plot that, I'd be down here. Then I'd go to the next one, and I know it would be a little less negative. And here, a little less negative, and a little less negative until I got to a tangent, a derivative of 0. Then over here, it's going to be positive, more positive, more positive, more positive, and even more positive. So it looks like this thing goes like this. And if you notice, it looks like it's going to form a line. Now, is that correct? We'll get to it, but we're just thinking about the geometry of it. Okay, let's go to the next one here and do the same thing. Let's look at every single one of these points and see if we can draw the tangent and what it would be. Well, this is a line, and that's a line. So we should know the slope of those. This is curved, this is curved, this is curved. So these are a little bit more challenging, where this, we know the slope. It's actually down one, right one, down one, right one. Down. Where? Everywhere. So we know for any one of these x values, our y, our limit, our derivative would be at -1. Where this is over 1 up 1, over 1 up. This is a slope of 1. So we know for any one of these x's over here, they would be a 1. So we would have a constant line going this way and at -1 this way. But what about at 0? Well, remember, the derivative is a limit. And remember, for limits, it had to approach the same y value about that x. And since we're looking at an x of 0, and it looks like it's approaching from +1 on the right, -1 on the left, then that means that the limit, and therefore the derivative, does not exist. Let me prove it to you graphically at this point. Here, there's only one way to draw that tangent line. Same thing with any and every one of these points. But for all of these that we drew that tangent to, look at this one, this sharp edge or corner. I could draw a tangent there, I could draw a tangent there, a tangent there, a tangent there, a tangent. Well, then which one of these is the slope of the tangent at that point? Well, they all are. And again, therefore, the derivative does not exist at that sharp corner. So again, the graph of this would look something like this, where we have a hole, and then it goes this way at 1 and -1. Graphically, this one looks something like that. What do you think? Since this was y equals x squared, this is y equals absolute value of x, what we're really trying to find is what the slope of the tangent would be, what the derivative would be. And here again, you can see positive, positive, less positive, less positive, less positive, until we get to the derivative equaling 0. Then it would be negative, 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 to a point. Then we got to switch sides, negative, negative, less negative. It got to a 0 again. And then it would be positive, more and more and more positive. So how would we graph that? Again, positive, 0, negative, 0, and then positive. And what we're looking at, remember, is for those x values. We are finding the y values, the limit of these functions we call derivative. Really positive up here until it gets less and less positive, until at -2, it was a 0, which this is where y is 0. Then it was negative, negative, more and more negative, until a point it then started getting less and less negative until it hit 0 again. So negative until a point, and then it started getting less and less negative until it hit that 0 again. And then it got positive, more and more positive. Looks a little something like that, which, if you notice, looks very close to, and quite possibly might be, a parabola. Now remember, what we started with was a cubic function of some sort. So hopefully you're noticing a pattern with these polynomials. When it was x squared, we had something like this. When it was x cubed, we had something like this. Any guesses what this one might be, which is a negative x to the fourth since it's facing downwards? Well, what might you find first? Let's find where our derivative is equal to 0. That would be here, here, and here. For those x values, I know I'd be crossing through the x-axis at those 3 points. So then all we need to figure out, if that's where our derivative is equal to 0, then that means it's either positive or negative in all the other places. So looking at positive, that would be these. So my y values would be positive and getting less and less positive until it got to 0. Then here the derivative, or slope of my tangent, would be negative. Negative until it got to another 0. So now it came down here and then went back to 0. And then positive, 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 until it got less positive and back to my 0. And then it got negative, negative, and really negative down here. Positive, positive, less positive, till that 0 here. Notice what this derivative function looks like is a negative, from left to right, cubic. So that's something that I wanted you guys to hopefully come up with. And if not, hopefully I helped you to kind of work through it a little bit. We will continue to work on this, so don't get frustrated if you didn't quite get that. Let me know if you need more help on it, or reach out to a classmate, a TA. somebody that's gone through this and see if you can understand it on your own or with help. And just to reiterate, remember when we are graphing those tangents, we're looking at our x values of our original function, and we're trying to find the corresponding y value called the derivative or the slope of the tangent at that specific value. Again, it will be critical that you understand this down the road, and we will be looking at these things called maximum and minimums, or those peaks and valleys, because remember, that's where the slopes of our tangents were equal to 0. So these are definitely important because it allows us to take relationships or functions and try to find the maximum profit, say, or the minimum cost. And that's when we're at our best, is having equations set equal to 0. We've been working since pre-algebra on how to do things like that. All right, so a little bit more terminology, vocab here, and then we'll continue to move on and wrap up this derivative as a function. A function is said to be what at A if f prime of A exists. Well, remember, this is the derivative, and the process of taking the derivative was called differentiating. So this is said to be differentiable at some point if that limit, or what we call for short, the derivative, exists. So see if you can fill in the rest of these blanks. You could probably guess a lot of them are the same. I just didn't want to give you one so that it gave you all. But a function is said to be differentiable on some set if it's differentiable at every point on that or in that set we're calling S. Lastly, a function is a differentiable function if f prime exists on its entire domain. So a little bit different than the first one. This one is saying at a point, or this one is saying on its entire domain, and this one was saying virtually the same thing, but just saying some set, any set S. So not the entire availability, but more a subset. So remember when we talked about continuity and a function being continuous meant graphically that when we put down our pen or pencil, we didn't ever have to pick it up anywhere. And there was a 3-step process to make sure that the function was continuous. Hopefully you remember the 3 criteria were that at that value, it exists. We got something out of our function. And as we approached that value A from both sides, the limit exists. And lastly, step 3, which is this and this had to equal one another. The nice thing about derivatives is that differentiability implies continuity. Now, you may be wondering why that's true. If we can just take the derivative, then we know it's continuous. Well, remember, guys, that differentiability, the process of taking the derivative, which is a limit, is why that exists or implies continuity. So that takes us to theorem 3.2.2. If we had a function and A is something that exists, it's in its domain, well then if that function is differentiable at that value, I know you guys are just going to fill in all the blanks with that word now, right? Then what does that say about our function at that value? As we just mentioned, differentiability implies continuity. So if we can take the derivative and we get a value at that value, A, we're calling it, then it is also continuous at that value, A. But what about the converse? What if we reversed it? Does continuity imply differentiability? Think about that for a second and think graphically. That's why we work so hard on all the previous classes about knowing a lot of those parent graphs of each one of those functions. And think of a continuous function. Or better yet, think of one that may not. We call it a counterexample. A continuous function that would not take the derivative and be able to, oh, hey, that's continuous. But remember, we said it's not differentiable at 0 because we can draw a bunch of different tangent lines, or better yet, -1, +1. And so therefore, at 0, we knew it wasn't approaching the same thing, and therefore the limit, or derivative in this case, did not exist. So unfortunately, no, continuity does not imply differentiability. So as we mentioned, if we were to look at the absolute value at 0, we knew that just because it's continuous does not mean it's differentiable everywhere. So where else might this occur? So there are 3 different things that unfortunately will not allow us, even though it's continuous, to be able to find a derivative of. So the first one we know, because of the absolute value, that's at a corner, or what we call a sharp turn. But 2 other places, or things that do occur that graphically will not allow us to find the derivative are, that one should be obvious, where it's discontinuous, especially a jump discontinuity. But another is at what is called a vertical tangent. Because although we might be able to find the tangent line, if it's vertical, then that means the slope is undefined. All right, so there's one more thing that we want to talk about and discuss in this section, and that is called a higher order derivative. What does that mean, higher order? Well, if we can find the rate of change or derivative of a function, well, then couldn't we find the rate of change that is changing? I've mentioned here, is there a limit, pun intended, to the number of times we can take the derivative? Can we just keep finding the way that something is changing compared to something else? Well, that's what we're going to explore very soon here. But for now, we'll just give you the definition of what are called higher order derivatives. So take a look down here at how we wrote the derivative of some function. We'll just call it y, whether it's a function or just a relationship. We wrote the derivative with respect to x, is how we say this, of our equation y, or dy dx, or simply put, y prime. Well, then if we took the derivative of that, any one of those, which remember are all equivalent, well, then what is the derivative with respect to x, once again, of our already found derivative? It's almost like we're just multiplying when we're actually doing a limit process. But if you just multiply it across, it would look like d squared y, and then you'd have dx times dx, or dx squared. But remember, we, to make it official, would have to have parentheses around that, so it's not actually multiplying. Remember, it is the process of taking the derivative of this thing, so the second derivative of that y, with respect to x twice. And so hopefully you guys can see a pattern, because we will write this in several different ways. So I'll just ask you for the second, third, fourth, and then we'll generalize it for the nth derivative. And I'm giving you 3 different commonly seen looks. So let's see if you can fill this out first. Then we'll talk about the application of this thing and what the position function's derivative yields, and then what the derivatives of those would also. Go ahead and pause it, see how much of this you can fill out, and then I will give you the filled in form. So here it is. Hopefully you're able to come up with some of those. Obviously, the fourth and nth derivative, you may not have had the parentheses around those, but the reason we do that is just to emphasize that it's the derivative and not y to the fourth. Because obviously, if we didn't have the parentheses, that's what it would mean, is y times y times y times y. Why don't we just keep putting those tick marks? Because it would just be too laborsome to count how many times you had the derivative. Let's just put whatever number it is in parentheses and call it the same. So obviously, of these 3 versions, our favorite is this, because it is by far the simplest. But there will be times that I'm going to ask you to write it like this down the road, and you will see why. But again, any of these are equivalent, and hopefully you remember that it is just simply the rate of change of one thing compared to another. Meaning, what if we found the rate that our position was changing with respect to time? Let's say miles in hours. Well, you know that would be miles per hour or velocity. And therefore, the first derivative, s prime of t, is equal to v of t, the velocity at some instant, some time. Well, then what if we found the rate of change of our velocity? Can you come up with what the second derivative would find for us? What if our velocity was changing? What would that mean is happening? Think about you being in a car. If your velocity is either increasing or decreasing, what does that mean you had to do? That's right. Hopefully you said accelerate or decelerate. And so in general, we just call it acceleration. Whether that be increasing your speed or decreasing your speed, the gas or the brake. And of course, if that's the second derivative, then it would look a little something like that. The second derivative of our original function, which we call the position function, s of t, and or the derivative, one more derivative, of what was our velocity. Well, we got how our position changes over time. That's velocity. We got how our velocity changes over time. That's acceleration. But what if your acceleration was changing when you stepped on the gas? Better yet, what if you stomped on the gas? Then not only is your acceleration changing, but it makes you jerk. So for lack of a better term, hopefully you guys aren't calling me that by the end of this class, that is what we call the rate of change from acceleration. It's our jerk. Now again, you can jerk forward or you can jerk backwards, just depends on whether you are stomping on the gas or the brake, how that acceleration and how drastically it's changing. So the third derivative would look like that. Higher order derivatives is something that we will get into, but we talked about graphing. We talked about defining a limit derivative as a function, and then the application here at the end using these higher order derivatives. It's a lot to take in. We got to practice and make sure that we go through some of these bumps in the road so that we can understand it at a higher level. Puns intended. If you guys haven't figured that out, that's Alan. I'm out. See you guys for the third section. Take care, everyone. Be well.